All right. So I believe I might have these switched, but I think this is right. Homework is due Wednesday. That's the 25th. And then we have our first quiz on Friday. Anybody have any homework questions before I get back to new stuff? Okay, do you have it with you? Anybody? Aaron, you're always dependable. Let's make that do next time. Yeah, that's a good idea. Okay, 15. Okay. This what on this is on yeah, what's it called? The rigid body kinematics? Yeah. Kinematics of particles in a regular coordinate system, number 15. Okay, so there's a Ferris wheel. And we're analyzing what's going on when the passenger is on the left side. We use a standard coordinate system. And there's a clockwise angular velocity of 1.5 radians per second. There's also a clockwise angular acceleration of 2.5 radians per second squared. The passenger's in the position shown. There's a radius of 5 meters. And it asks for a few things. First, what's the velocity vector of the passenger? So let's call that P. What's the velocity of that passenger P, assuming the center is at rest? Well, that's just regular circular motion. And so the velocity is just equal to the angular velocity crossed with the r vector. And this r vector goes from the center of the circle to the passenger. Oops. All right, so if the angular velocity is this way, then put your fingers in that direction. It says that the direction of the angular velocity vector is into the page. Is that a positive or negative z direction? That's negative z, because if you go right-hand rule from x to y, it has to be positive z. And so that vector omega is 0, 0, negative 1.5. And now we need a vector going from the center of the circle to P. It has a magnitude of 5 meters, and it's going in the negative x direction. So negative 5, 0, 0. Take that cross product, and you get 0, positive 7.50. At first you look at it, cross product, and think it's a negative, but then remember y always has to be a little bit weird. And this is meters per second. So does it make sense with the way everything's drawn that we got a velocity vector in the positive y direction? It's spinning this way around the center. And so at that point, the velocity vector has to be tangent to the circular path, in the direction it's moving, so it has to be positive y. So that our intuition checks out with the math.
You go from a unit of radians per second to a unit of meters into meters per second?
Because radians is sort of a fake unit, radians are really pure numbers. So we could really write that angular velocity as 1 over seconds, and angular acceleration is 1 over second squared. So yeah, just anytime you see radians, that's just there to remind you that you're talking about angles, but it's really just a pure number. Yeah. Yeah. So the rules for a right-handed coordinate system, which is every coordinate system we're going to use, is if you take the cross product of x and y, it gives you z. If you take the cross product of x and z, it gives you negative y, because y always has to be the weird one. And if you take the cross product of y and, should have written that k. Take the cross product of y and z, it gives you x. So those are the rules. So right-handed, use the right-hand rule in that order. It has to put your thumb in the positive z direction. If you do the right-hand rule from x to z, it has to give you the negative y direction. That's how we, that's how we knew that the right-hand rule, so the right-hand rule tells us if the angular velocity is this way, the angular velocity vector is into the page. Okay. But then in order to figure out whether that's the positive or negative z-axis, that's based on those rules for the coordinate systems.
I just want to say, if it goes into the board, then I could just say it's negative. Is that safe?
Well, it's safe if x and y are drawn the way you're used to. If x was drawn the other way, if it was like a flipped version, then z would be going. So it's probably a good habit to get into, to be a little careful. We'll do some problems where the coordinate system will, I'll give you a z and a y or something, and you have to figure out what direction the x is.
I also want to just forget about z, but in this scenario, we know that you have a z because just the way that these problems work out.
Well, yeah. So any problem where there's rotational stuff happening in the plane, any rotational stuff deals with axis of rotation. And so if there's rotation happening in the plane, the axis of rotation has to be parallel to the z-axis. It's the axis, like if you imagine there being a hinge here that's allowing this rotation to happen while it's going this way. The orientation of the hinge body itself would have to be this way to allow that motion. And you can think of the axis of rotation as being the body of the hinge. Or the body of the pin, if you think of it as some kind of more basic pin joint. If the
X and Y.
if X and Y are not flipped from this. Yep. As long as you have to go counterclockwise to go the shortest distance from X to Y, you know what I mean? Then Z is coming out of the page. Okay, and then the second part says what's the acceleration? We want to calculate the acceleration of P. And again, the center isn't moving. The acceleration of that point is equal to alpha cross R plus omega cross quantity omega cross R. All ripe watermelons will rot. It's not very useful as a way to keep yourself upbeat about watermelons, but it is helpful for remembering the order of the vectors in that. Actually, I think I said this last year or something, and the guy was like, "That's so like negative. What about all ripe watermelons will rot?" Will rot. Will rot. That's more sort of factual, yeah. Right. They roll. I don't know. Maybe we can test that later. Maybe we can calculate that. But anyway, so we already have omega and R, so we just need alpha. And we'll think about that the same way. If it has an angular acceleration that's clockwise, then do your fingers clockwise. Your thumb is giving you the direction of the angular acceleration. So the angular acceleration vector is 2.5 in the negative z direction. Radians per second squared. And so the acceleration is 0, 0, negative 2.5, crossed with the r vector we had before, negative 5, 0, 0, plus 0, 0, negative 1.5, crossed with the quantity 0, 0, negative 1.5, cross negative 5, 0, 0. This is the calculation that we did for the velocity before. That'll happen that way pretty often. So 0, 7.50. These two crossed give you positive 12.5. And so the acceleration of P is 0, 12.50 plus 1.5 times 7.5 in the x direction is 7.5. What is that? Oh, that was one of the 4 things I was thinking it might possibly be. Okay, so that's, what did I say, negative? Positive. 11.2500. And so the total answer is 11.25, 12.50 meters per second squared. Okay, so now let's think about if this direction makes sense. And the way to think about, the way to sanity check the acceleration in circular and spherical motion is to remember that this one is the tangential acceleration, and this one is the centripetal acceleration. So first, does it make sense that the tangential acceleration is in the positive y direction? Yeah, because the angular acceleration is this way. So the tangential acceleration has to be tangent to that circular path in the direction of that makes sense with that tangential with that angular acceleration. And then the centripetal acceleration is in the positive x direction. Does it make sense that the centripetal acceleration at that point is positive x? Yeah, because it has to go from the point toward the center. So that doesn't guarantee that we have the right answer, but it's encouraging. It's a nice thing to take 30 seconds to check. Does the tangential and the centripetal go in the right direction? And then the last one, okay, well, this one slipped by me. I really shouldn't have assigned this problem yet, but it's only the last part. So part C says, what's the acceleration vector if the center of the carousel has an acceleration so what's the acceleration of P if the center has a translational acceleration of 5, -3 meters per second squared? This is the next topic we're going to talk about is relative motion. I mean, you talked about that, I'm sure, in passing in Physics 1, but you don't spend a lot of time thinking about it. But do you remember? So relative motion says the acceleration of P relative to the ground, that's what we want, is the acceleration of P relative to the center. That's the acceleration that P would have if the center wasn't accelerating, plus the acceleration of the center relative to the ground. That's what we're given. And so, this notation takes some getting used to, but the idea is what you might have thought it would be. You just end up adding that extra acceleration on. So the acceleration of P relative to the ground is equal to the acceleration of P relative to the center. That's what we got up above. Plus the acceleration of the center to an observer on the ground. That's 5, -3. And so the total acceleration is 16.25, 9.5 meters per second squared. Okay, so what we're talking about there is like if this Ferris wheel was on I'm not going to draw it, but if the Ferris wheel was on a truck or something and the truck was accelerating while the Ferris wheel did its thing, what's the total acceleration of the passenger? Why would you care about that? Why not just, what would be wrong with just using the acceleration of P relative to the center of the Ferris wheel if you needed the acceleration? It's actually it's more important than that even, because Newton's laws only work if you're dealing with an inertial coordinate system. And so in that case, you'd be calculating the acceleration in a coordinate system that's accelerating, and Newton's laws don't hold in that case. So in order to use Newton's laws, you have to represent your accelerations in a coordinate system that's not accelerating or rotating. Yep. Yes, but not very much. Yes, that's a good question. Mm-hmm. Yeah. It's easier to think about in terms of velocity. You know, acceleration is hard to picture, but imagine you're on the ground at a train station filming a train going by. Say the train's going by at 5 meters per second, and somebody's running from the front of the train to the back of the train, and you're filming it. You just see the person standing still while the train moves. And that's what's happening. That's what would be happening there too. Yeah, let's see. Yeah. Uh-huh. So if, yeah, so in an inertial coordinate system, then there's no kinetic energy, and work is a change in kinetic energy. So yeah, that's right. Yeah, exactly. Right. Well, you still have to, you know why the treadmill is hard? Like, let's not get into it.
I'm going to be curious.
Well, okay, so like, don't you sort of have this feeling like on a treadmill, you're not really doing anything. You're just like sort of, you know, yeah, all you're trying to do is get your legs up. But really like the work of running is not really about keeping your motion going. If there was no air resistance, that would be true of running too. Really the energy you spend running is doing a small number of things, like, which are getting your body up high enough that you can get your leg that's backwards all the way to the front, you know, and keeping your body from tipping. I think really those are the two main things. And so, so yeah, if you were running with no air resistance, that it would be equally true to that feeling that you have like on a treadmill. There should be a way to cheat what's going on because you're not going anywhere. Well, that's really true running down the street too if there was no air resistance. So running on a treadmill is exactly as difficult. So if you're ever trying to make sense out of like how hard it is to run on a, you know, to run a certain speed on a treadmill, running on a treadmill is exactly as difficult as running that fast on the street with a wind behind you at exactly the speed you're running, you know. So if you're running really fast, it can make a big difference because you imagine like a 10-mile-per-hour wind down on the ground is a pretty stiff wind, you know. Yeah. And then also some people just can't do it because they're like tense up, you know. A what? Oh, I thought you meant like on the Quality Products Network or whatever. Oh, this will make the time fly by. All these beautiful watches. Well, I used to be a runner long ago, and I was running on a treadmill one time, and I don't know. Yeah, it's more fun to be outside, but you sort of get used to it, and you're just watching TV or whatever. But I was like watching a hockey game, and I wasn't paying attention, and I've been going for like a long time, and all of a sudden I was just like lying on the ground, and I'm like, ah, and my foot had just landed on the side, and I just got like right over the railing. What happened? It's really a shock when you're. Any other questions about this problem? Any other homework questions? Okay. All right, well, let's talk about relative motion. Relative motion, the idea is that we're talking about tracking motion in two different coordinate systems. So imagine two non-rotating coordinate systems with the same axis orientations. How do the observations of a single object made in these two coordinate systems compare? And I think the best way to intuitively think about what an observation in a given coordinate system is, what it means, is to think of a coordinate system as a video camera. And imagine that everything you're watching, you're watching it in a room where all the distances are marked out or whatever. On the video camera, you could measure the position of things, you could measure the velocities of things based on those positions. And you could, it probably wouldn't take you too long to think about how to do that if you had a room where every location was you were able to assign a number to every location. And so let's think first about positions. So let's say that we have a coordinate system A, and a coordinate system B, and both of these are being used to observe a point P, a particle P. Well, let's think about free vectors. That's position of P, that's the position vector according to this video camera at A. Okay, so if you measure, yes?
In my mind, this is all on the same Z?
Yeah.
Okay.
It doesn't matter actually, 3D, 2D is the same, but I'm imagining doing it in the plane, yeah. Okay, so we have to come up with a name for the position vector of P observed in this coordinate system A. Let's call it position of P relative to A. Okay, so it looks like that fraction symbol. And then what does the video camera at B see? It sees this vector. That's the position of P according to B, or we say position of P relative to B. And then I'm going to draw one more vector from one origin to the other one. So what would you call this in this notation? The vector I just drew. Like position of something relative to something. Yeah, position of B relative to A. If I had drawn that vector the other direction, it would be the position of A relative to B. Say, for example, just the way people talk about it, the position of P relative to A. Then, just from vector addition, you can see that the position of P relative to A is equal to this one plus this one. You can, that's what vector addition is. You put them head to tail, and right. So the position of P relative to A is equal to the position of P. I am going to write it this way: position of P relative to B plus the position of B relative to A. And the same idea works for velocity and acceleration. The velocity of some object relative to A is equal to the velocity of some object relative to B plus the velocity of B relative to A. And same thing with accelerations. The acceleration of P relative to A is equal to the acceleration of P relative to B plus the acceleration of B relative to A. You can think of it in terms of vector addition like this, but as sort of a quicker memory device is to think about fraction multiplication. It doesn't have any basis in mathematical reality, but it gives you the correct answer. So think fraction multiplication. So for example, in this case, P over A is equal to P over B times B over A. The B's cancel out and you get P over A. One thing to keep in mind about this, notice, in this class, inertial coordinate systems are going to be a big deal. So we'll think a lot about whether a coordinate system is inertial or not. What are the two ways a coordinate system can be non-inertial?
Inertial?
Yeah.
Okay, so, well, that's what I'm going into, but I was just checking to see if anyone remembered. So, non-inertial coordinate systems have either an accelerating origin. So imagine if you picture a coordinate system as a video camera, imagine taking measurements with a camera that's accelerating. And or the coordinate axes rotating. Relative motion doesn't help when the coordinate axes are rotating. So it isn't useful for rotating coordinate axes. But it is a way to I want to say this. It is a way to, let's just say, deal with an accelerating origin. Okay, let me do an example. So let's say there's a passenger running on a cruise ship. And there's a camera on the ship that you can use to take measurements of the person running. So according to a camera on the ship, the passenger's position vector follows this function. Position vector is a function of time equal to 80 times the cosine of 0.01t, 80 times the sine of 0.01t. And then according to an observer on the shore, a camera on the shore, the ship's position vector follows the function p of t is equal to t for the x component and 0.05 t squared for the y component. And the question is, what's the acceleration of the passenger in an inertial coordinate system? Well, why would you want that in the first place? Because Newton's second law relates acceleration to force. So if you're trying to calculate any kind of forces, you need to know the acceleration, or that's a way to do it. But you can't use Newton's second law in an accelerating coordinate system. So the problem is we have this measure of we have an easy way to get the acceleration of the passenger according to the ship. The ship is accelerating. So we're going to have to use relative motion to figure out the acceleration of the passenger according to the ship. We can figure out the acceleration of the ship according to the ground. And then we can use relative motion to connect those two. So relative motion says the acceleration of the passenger relative to the ground is equal to the acceleration of the passenger relative to the ship plus the acceleration of the ship relative to the ground. And you can check that the fraction multiplication thing works out to make sure that you have an acceptable order. Yeah, the ships would cancel out and you'd be left with passenger over ground. So that works. I don't know. I've never thought about it that way. Okay, so we're trying to find this. We have to do it by calculating these two things. So acceleration of the passenger relative to the ship. Well, we know that the position of the passenger relative to the ship is 80 times the cosine of 0.01 t, 80 times the sine of 0.01 t. And so from that we can get the velocity of the passenger relative to the ship by just taking the time derivative. So that is negative 0.8 sine of 0.01 t and positive 0.8 cosine 0.01 t. And then we can get the acceleration of the passenger relative to the ship. Take the derivative again, and you get negative 0.008 cosine of 0.01 t, negative 0.008 times the sine of 0.01 t. And that's the acceleration that's measured by the camera on the ship. It's not inertial. And now we can use what we know about the ship's motion relative to the ground to figure out the acceleration of the ship relative to the ground. The position was t, 0.05 t squared. So the velocity of the ship relative to the ground is 1 0.1 t. And the acceleration of the ship relative to the ground is 0.1. So now we can put these together. The acceleration of the passenger relative to the ground is equal to negative 0.008 cosine 0.01 t, negative 0.008 sine of 0.01 t, plus 0.1. Any questions about that? Relative motion goes together really naturally with circular and spherical motion for two reasons. One is that even if it is just a single particle that's moving in spherical or circular motion, often the center of that circular or spherical motion is a physical thing causing it, like a cable's connected to a thing or something. And so that physical thing can be accelerated and tracked. And then the other reason, maybe the more important reason for us, is that rigid body motion, anything in rigid body motion, if you're tracking the motion of a single point on a rigid body, that point is in circular or spherical motion around whatever the thing is rotating about. Sometimes you treat it as the center of mass, sometimes it'll be an actual physical point. And so if the rigid body is translating through space at the same time that it's rotating, you're often going to use circular and spherical motion to track the motion of the particle relative to the center, and then use relative motion to add on the center relative to the ground. Okay, so I think most of the example problems, the homework problems, involve circular and spherical motion, where you're given something about the motion of the center of that circle or sphere, and you're given something about the motion, the angular motion around it. That was like that first example I did at the start of class. Okay.